Good morning, everyone. I will be presenting about AutoCheck, shift left using AutoCheck formal verification. First, I want to acknowledge my co-author Sam from Siemens, who has been helping me and cooperating for not only for formal verification, also for simulation, Questa VIP, and everything that I've been working on. So thank you, Sam. Probably shift left, you've seen at least 1/3 or 1/4 of every presentation and every article talks about shift left. So it's an important area that every EDA vendor and more semiconductor companies are trying to do. I'm going to talk about AutoCheck with informal verification and how I'm using this for better quality and faster completion. So about three areas, three things that I'm going to talk on the agenda. I have a couple of slides about Lockheed Martin. As I was, somebody made a comment a couple of weeks ago that they didn't know that Lockheed Martin actually does FPGAs and ASICs. So I'll talk a little bit about that. I'm going to talk about formal verification and the AutoCheck specifically. But the most important part is the third part, which is an actual example of a bug that was found by AutoCheck. So I ran AutoCheck, we fixed a few things, but then I've put the report in our repository and it was there. And then the same bug I found through simulation, and it took much longer, much larger effort to debug. And then I looked back and I said, well, let's see. And it was there in the AutoCheck report. So I'll try to do a comparison and to show why it is important to run early, to run formal, to run AutoCheck, and get rid of most of the bugs and fix them, or at least know about them and waive them. Okay. So I work for Lockheed Martin. Lockheed Martin has a very large number of customers, domestic and internationally. We do two major type of projects. There is aerospace and defense, and there is commercial products. We have four major business areas. Maybe other companies call them divisions. We call them business areas. Aeronautics, missiles and fire control, rotary and mission systems, and space systems. So these are probably the pictures that are best to represent that. This is all information that is public. There is nothing classified or confidential about here, and any additional information that you might be interested, you can find or ask our company to provide. I'll try to be fast, so I'm not going to talk much about the other three business areas, but I'll talk about space, Lockheed Martin space business area. That's where I work. Actually, that is a depiction of the Orion crew module that will take the astronauts to the moon and then to Mars. And I can proudly say that I worked on one of the FPGAs on the Orion crew module. So in the Lockheed Martin Space BA, what we do is both the satellites and the spacecraft that go into space, and also the ground stations that communicate and control the things that go into space. Silicon Solution is our organization. That's where I work. We do ASIC and FPGAs, develop, design, verify documents. We do the vast majority of the FPGAs and ASICs for the space business area. There are other organizations in the other business areas that do similar stuff. We tried our best to cooperate with those also. So I'm part of this organization. And I'm going to go kind of to the second half of my presentation, which is about formal and specifically about AutoCheck. So I'm very passionate about formal. I've been using and I use several of the formal verification tools. And recently I've been told, but I want to stress that AutoCheck is becoming inspect. So I use AutoCheck, cover check, connectivity check, prop check. Very little I used in the past, register check, and verify trust. All these tools coming either from classic Mentor zero-in or from OneSpin tools that you've seen. They are integrated now with the Questa formal verification. So Questa AutoCheck Inspect is one of the most automatic apps, and I'll show that. Basically, all what we need is the RTL and a tickle script with a few commands. And I will dive into the details of AutoCheck. If that's okay, can I see a show of hands? Have you used or are using either AutoCheck or Inspect? Okay, then I'll talk in details about this. So, in a nutshell, AutoCheck Inspect is for formal verification from Siemens CDA. It's a bug hunting tool. I'm stressing that it should be used early in the design process. It's automatic. It will find RTL functional errors. And these are just some examples: dead code, combinational loop, state machine unreachable states, deadlock and live lock, arithmetic overflow, underflow, and so on. It's very good to be used early. And the other thing that I need to stress, although that's true for most of the formal, it does not need a test bench. It does not need test. It can be used as soon as the RTL compiles. So that's a major benefit that we need to take advantage of, not to use it late. Then we can integrate with whatever CI/CD we want and have run AutoCheck on every RTL change. It's important to stress that is much more than lint. It uses formal engine, and the lint is not using formal engine, so it can explore sequential behavior of the design. We don't need expertise in formal verification to use this. It's one of the things that can be used without a whole lot of expertise in formal, and it can run at different levels of hierarchy. So that's probably, in a nutshell. Okay, so that's what I was trying to stress. We have the RTL, and that's about it. That's what we need. We're going to write a tickle script or include a few commands in our make file, and we can run AutoCheck. And then we go back in the loop, and we can have waivers, fix some of the stuff, some of the findings, and so on. So there are simple checks, and this can save weeks of simulation work. All right. It's very good, and we need to stress that the flow starts with the same compilation flow as the simulator. So as soon as we have a design that compiles correctly, we're going to use the same compile to start AutoCheck. vlog, vcom, we get a work library, and we can do either the simulation or the Q verify for AutoCheck. So the very first step is the same, and as soon as we can compile, we can run AutoCheck. All right, the results. So the results coming out of the tool are really in two categories. And the first one is compile time checks, and the second is more of verify time checks. The first part, the first list of issues found through compile maybe can be found by other tools, and mostly by lint, but also other tools. The second list of issues at the verify time, those are issues found through formal engines. They're not going to be found by other tools that are not formal. They don't use the formal engines. So we have a few columns. It shows how many evaluations were done, how many were found, and how many we waived, so we can use the waivers. Maybe I'll focus on FSM lockout state. So there were 19 evaluated, and 3 were found as issues that need to be reviewed. And again, these are the results, the categorization of the results. The violations are must fix, the caution, potential problem, inconclusive. The tool, in the amount of time given to run, could not determine if there is a violation or if that specific check has cleared. And evaluated, no problem was found. So very similar to other tool, we have violations and cautions like errors and warnings. These are just some examples actually from the manual that can be found online or just with the help when you open the GUI. The only thing that I wanted to stress here is it shows, of course, it describes what is the issue, what is the error. It shows the default. It's a caution, so it's kind of like the warning. It shows that by default, this one is specifically off, so you need to turn it on if you want it. And the stage is verified, so it's in the second stage. Similarly, another one, bus value conflict. Again, it's a violation, so it's an error. It is by default on, and the stage is verified, as I was showing previously. The GUI is very familiar on the left with the hierarchy. On the bottom, we can see the transcript and the RTL on the right. And again, the visualizer GUI that we are familiar with from simulation and from Siemens. This is the advantage. So in the formal, if we get a failure or an issue that is flagged, it shows a counterexample. This is very much easier debug than in simulation. In simulation, I get a failure. I need to decide in the waveform which signals to trace. How am I going to debug the simulation failure? Here, it gives me exactly the counterexample. What are the reset signal, the property signals for the property that failed, and most importantly, the contributors. So automatically, the tool shows me what signals to look at, how they change in order to get to this error issue. So the counterexample helps in debug. It's more efficient debug. How do we get there? We get through using makefiles. That's probably the easiest thing. In our organization, we have other scripts that are internal. They're basically, I'm going to show, there are 2 most important commands, the compile and the verify. And it is important, it is good to to set the clocks and the reset, although the tool most of the times infers correctly the reset and the clocks. This is an example of the commands, and again, I'm stressing here in yellow. Basically, there are two important commands, and then you can build upon that. Once you do, so first we do the vlog vcom, and then the AutoCheck compile, AutoCheck verify, and then we can start the GUI and see the results. Everything else can be built afterwards. Black boxing is important like in every other formal, so every time we need to do that, and sometimes the tool will black box some of the modules when those are not available. We have to be careful with the black boxing because with the black boxing, a passing property is correct, a failing or a failing with warning, we have to be careful because the black boxing introduces cut points and there may be false failures. Okay, and that's probably the most important. I hope I have a few minutes. 2 minutes. So that's the bug example, and I want to compare AutoCheck formal with the simulation. So for the simulation, of course, we have to do the vlog vcom at the beginning, but then, and this was the case, I have to configure the Questa VIP, generate the UVM test bench and the UVMF, configure the test bench, connect the DUT, generate the RAL. This specific bug I found with the RAL. So generate the RAL package, create the test, use the RAL sequences. They have their own quirks, run and debug the failures, and the debug was long and complicated. And again, thanks Sam for all the cooperation. So that's the simulation is a long process and debug. Formal AutoCheck. The compile is the same, so we start with the same. We develop the make file or the commands, and we can start with 2 commands, and we need to add a little bit more, especially if we do FPGA, we need the right library. Sometimes we need to do the reset and the clock, but it's basically anywhere between 2 to 5 commands on the tickle script. We're up and running. We run, we see the violations, we refine and go to that. So as soon as the RTL is ready, we don't need the test bench, we can run this with a few commands. These are the details of the bug, and as I was saying, I ran the AutoCheck, I've put all the results in the repository, and then I found this bug later, and I was like, let's look if the AutoCheck found it. What was the issue? There are a few bits in the UART control registers that were not initialized. So it's an IP. The IP vendor did the right thing. A bunch of bits are initialized always, and a bunch of bits are initialized only when the customer does a specific setup. And we thought that we did that, but it wasn't correct. So there are a bunch of bits from the control registers that were not initialized when we do the read. So it's a read from an HB master, goes through a bridge to APB, comes back. The APB gives X's on a few bits. If we do simulations with 2 values, it comes back as 0, so that's not really a good indication. But then we have all the assertions that come with the VIP, and the assertion flagged X. And then by debugging that, it's a specific one of the bits that says that what happens when the FIFO is empty for the UART. So it was a long, long debug effort. AutoCheck. AutoCheck already found this. AutoCheck said it's an X unresolved, and it's in the UART, and it's in this specific bit names, and that's where it is. It's there. So we can find bugs early. As a result, we shift left. This is a little bit about shift left. You probably have seen it, and as I was saying, 1/3 of 1/4 of all the presentations on the article, not only in the EDA, but in the semiconductors. That's the summary what I was trying to stress. It's going to help reduce project schedules, and it's going to improve productivity. It's easier to debug and to find early. And it's not going to replace simulation. We need both simulation and formal. And it's exhaustive. Every presentation talks about exhaustive. Okay. The change names, the name is changing to inspect. I try to stress that. This is my contact information. If you have any question, if it's not something confidential to Lockheed, I'll answer. And I want to thank you for allowing me to present.